Good morning to all. So today we will be discussing on ceramic materials and their structure and properties. Okay. So in this part of discussion, we will be addressing certain materials which is we call ceramics. Okay. So these are material which is non-magnetic and most of them are behaving as insulators. Okay. And glass is one of the ceramic example we can see. And when you see the different class of ceramics, so these are the different type of ceramics one can see. The glasses, clay products, refractories, abrasive, cements, and advanced ceramics are there. And glasses are normally we'll be using for optical properties and containers. So it will be using as a containers we know already. And clay products which is used to made of bricks, whiteware. Okay, so different of material like ceramic material, ceramic plates and all which is made up of clay products of ceramic. And then we'll be having refractories. These refractories means these are kind of bricks which will be having high temperature furnace to prepare. Okay, and there are abrasives, so which is the ceramics we utilize to made sandpaper, cutting and polishing purposes. And there is also ceramic which we call cement. We already know that cement, that is we are using for as a building material. So in that, which is also a ceramic and which is we normally call it as a composite. Okay, in structurally also it will be having two different combination will be there, so we'll be discussing later on. And advanced ceramics which are utilized to made rotators, valves, bearings and sensors. Okay, so these are the six different types of ceramic one can see. Okay, now we'll just see what is glass ceramics and the other ceramics. Okay, so here the melting temperature for glass is moderate, so it will be large when you consider in the ceramics. And also for a ceramic case which will be having a low toughness and ductility and will be having large moduli and creep resistance. We already talked about creep resistance when we discussed about the fractures, like plastic deformation and fractures. When we discussed there, we discussed about creep resistance. Okay, in glasses, so we know that glasses are which is made up of normally silicate or borosilicate glasses are available, which are non-crystalline and which is in the amorphous form in the most of the case. So which is containing the other oxides such as calcium oxide, sodium oxide and K2O, potassium oxide and alumina A2O3. So these are the utilized in order for the application of different optical materials such as lenses and fiberglass and containers also made up of using glasses. And here you can see that different silica. Okay, different silicas made you can see over here, and which is fused silicas are there, which is where we'll be having a 99.5 percentage of silicon oxide in the content, and which is high melting temperature and very low coefficient of expansion which it will having. Okay, and when it comes to Vico, which is 96 percentage of silica, and we have borosilicate glasses are there where we'll be having 81 percentage of silica. In addition to that, we'll be having 3.5 percentage of sodium oxide and 2.5 percentage of alumina and boron oxide 13 percentage. So which will be normally used for the thermally shock and chemically resistant material like oven wares and all, which is made up of borosilicate ceramic. Okay, and the familiar one to us is containers, different containers which is having a 74 percentage of silicate, and in addition to that there will be a sodium oxide, calcium oxide and alumina, and also there will be a magnesium also will be presenting in the composition of a different type of glasses. Okay, and there is optical flint glasses, which is normally used in our lenses, optical lenses, that will be using as a spectacle and all. So we'll be having high density, high index of refractions will be there. And there will be glass ceramics. In glass ceramics, again you can see the percentage of silicate is varying, and there is more contribution from alumina, Al2O3 you can see. And in addition to that, there is a titanium oxide and arsenic oxide also present. So which is normally utilized to use as a oven wares again. So which is we call it as glass ceramic. Already I said that glass ceramic having a higher melting point compared to a glass. Okay, so that's a important one. So these are the different type of glass application one can see. So which is basically a silicate, a majority will be a silicate, and there will be added composition of calcium oxide and sodium oxide in order to get different property and different composition of glasses. Okay, so that is all about this particular slide. And when you can show that any non-crystalline glasses can be made to crystalline by the proper high temperature heat treatment. Okay, so in that way we yield a fine grained polycrystalline material, which is often called as a glass ceramic. Okay, and when it comes to glass ceramic, so I already said that glass ceramic perspective, where we can see the properties are, which is relatively high mechanical strength and low coefficient of thermal expansion, high temperature capabilities, and good dielectric properties and good biological capability, and which is normally used as application purposes or oven wares, table and oven windows, and which is of a strength and excellent thermal resistance. Okay, that's why we will be using glass ceramic for using as oven wares and table wares. Okay, and you cannot suddenly you cannot utilize, it won't break it out. Okay, and when in terms of electrical insulators, glass ceramics is basically an insulator, so which will be a substrate to print the circuit boards. Okay, we know that when you are coating any thin films, we need a substrate. Okay, so glass ceramics will be utilized in order to have a substrate to print the circuit boards. Okay, and which are heat exchangers and regenerators. So in those purpose also we'll be using this glass ceramics. Okay, and now we'll go to refractories. We know that this is one of the type of ceramics, so which will be having the capacity to withstand high temperature without melting or decomposing. Okay, and which will be remain unreactive and inert when exposed to severe environment. Okay, and also which will be able to provide a thermal insulation. So that's why refractors are more important. Here you can see the a kind of a phase diagram which is representing the alumina oxide composition that is varying in a silicate. Okay, so silicate is a majority part, and with respect to the composition of alumina in the silicate, will have different phases. Okay, so that phase diagram has represented in this figure, so which will be having a higher melting point when the composition of alumina is more compared to the lower composition of alumina. Okay, so that you can see from this phase diagram, you already know how to analyze a phase diagram, so I am not going very deep into that. Just only want to say that which is high, having high withstand capacity in order to go for it. Okay, so upgrading the alumina content will increase the maximum service temperature. Maximum possible temperature can be obtained by using this one. And the application of this kind of ceramics, the refractories, so which is application including the furnace lining for metal refining and glass manufacturing and metallurgical heat treatment and power generation. In these regions we can actually extensively we can use these kind of ceramics. Okay, so these are some of the kind of refractory types has been listed in the table: fire clay, high alumina fire clay, silica, periclase, and periclase chrome, like you can see. And in each one you can see the composition of different uh, oxides element you can see in the list. Alumina, silicon oxide, in each percentage is listed in the table very clearly. Okay, so with respect to the percentage of different oxide composition, there will be having a different type of refractories can be obtainable. Okay, and here you can see that one of the application will be having high tension lines, transmission lines will be using, and high temperature furnaces will be using. And the third one, so third one in the class of different type of ceramics is abrasives. So the properties of abrasives, normally it is used for wear, grind and cut away other materials which is necessarily are softer. So these materials are softer, okay, and the hardness, the normally diamond, tungsten carbide, alumina oxide, silica sand, which are normally is the different properties in the corresponding materials in this list. Okay, so we are resistance can be made up of silicon carbide and tough material like tungsten carbide. Okay, we are very familiar with the tungsten carbide. We have discussed the same when we discussed about phase diagram. Okay, hope you remember that. And now the application, so it is normally used for grinding, polishing, cutting and drilling. Okay, so the polycrystalline diamonds in a resin matrix you can see in the figure, and the coated single crystal diamonds you can see, and oil drill bits. Okay, we know that drilling bits of in oil refineries, and cutting blades. In all these applications we normally use abrasives. Okay, and now the fifth one, that's about cements. So cements are the how the characteristic feature of this material is that when we mix it with water, we know that already, right? When we mix it with the water, they form a paste, and subsequently it is sets and harden. So that was a property of a cement that we already know. So that was a main characteristic feature of a cement as well. Okay, and we know that there are different type of cements. The Portland cement is consumed in the largest tonnage, we know that, and the principal constituents of a cement are tricalcium silicate, okay, and dicalcium silicate. So these are the two composition, calcium oxide and silicon oxide are mixed to obtain the cements. Okay, and now it comes to the fabrication and processing of a ceramic. So this has, I'm not much detailing, but let me just introduce you that the ceramic fabrication techniques, especially the glass forming process. The glass forming process are pressing, blowing, drawing and fiber forming. Okay, now if you want to for the particulate forming process, that is like refractories and the kind of abrasives, in order to form, we will be using particulate forming process, which is called powder pressing, which has three-way: hot, uniaxial and isostatic. And the other one, it is hydroplastic forming and slip casting, tape casting, and further we'll be having a drying process and firing. So that is the process of preparing the refractories and abrasives. And now the third one, it is about cementation. So it's a process to prepare the cement form. Okay, so these are the three major process: glass forming process, particulate forming process and cementation. So these are the main process. Under that there are different processes are there to form ceramics. Okay, so I'm not very detailing each one. Okay, so now it's not that part of the discussion of as of now. Okay, so we'll now look into the structural aspect. So we mainly discussing the structural aspect of different ceramics. Okay, so when you talk about ceramic, especially the bonding perspective, so mostly the ceramics will be having ionic bonding, and some are also covalent also there. And we can say that the percentage of ionic character increases with the difference in the electronegativity of the components in the material. Okay, so which is having large versus small ionic bond characters will be there. And you can see that mainly when you talk about silicate, we normally having a silicon, right? and which is a high electronegative one, and we will be having a calcium, and which is making a bonding normally with oxygen or fluoride, fluorine or chlorine like fluorides. Okay, and you can see that here how we form. So it's an ionic bond character normally will be made of calcium fluoride CaF2. So will be calcium will be having electropositive and the fluorine will be electronegative, and calcium F2 will be larger in that situation. Okay, so the ionic bond character will be large for the case of calcium F2. Now let me just introduce you silicon carbide formation, where a silicon and a carbon, it is combined to form a silicon carbide, and the ionic bond character will be small in that case. Okay, so this is how it happens. Now the ionic bonding and the structure. Okay, first of all, for a stable structure, so we need to maximize the number of hash means number of nearest oppositely charged neighbors. Okay, so you can see that the unstable case, the nearest oppositely charged neighbors are closely bit farly placed, that will be unstable, and these are the two conditions where we'll be having the stable condition where the positive and negative ions are placed comparatively in a nearer manner, and the ionic character will be very large in that situation. So here you can see the net charge in the structure should be always what? It should be 0. Net charge of a ceramic should be always 0. So here you can see an example of calcium fluoride, where we will be having calcium 2 plus cation, and which is combined to form two fluorine F minus and F minus, which are treated as anion. Okay, so these are the ionic bonding structure will be look like, and here the blue one in this representation you can take it as calcium, and the green one you can take it as fluorine. Okay, so similar case you can also see in the case of silicon oxide, magnesium oxide, and silicon carbide, and aluminum oxide as well. Okay, so similar structure formation will be forming there as well. And here you can see the coordination number and the ionic radii in a ceramic case. So the coordination number is increases with the radius of cation with respect to anion. Okay, so how many anions can you arrange around a cation? So here you can see an example of the ratio of cation, the radius of cation with respect to radius of anion, which is given on the left hand side. On the right hand side, the coordination number is given, and the different type of arrangement, that is linear, triangular, tetrahedral, octahedral, cubic arrangements has been specified over here. Okay, so in each case the radius of the particular structures is mentioned over here. Okay, so here you can see the zinc blend structure, which is zinc sulfide and sodium chloride and cesium chloride structure you can see, and each having different type of coordination between the anion and cation. So here the geometry is tetrahedral, and when it comes to sodium chloride, the arrangement between sodium and chloride, it is octahedral. Okay, when it comes to cesium chloride, the arrangement between the atoms, the cation and anion, it is in cubic manner. Okay, so you can see the number of, in linear we'll be having 2, in triangular we'll be having 3, and for tetrahedral we'll be having 4 around the anion, and it will be 6 for octahedral, and 8 in the case of a cubic arrangement. Okay, now how do we select the site selection? So it depends upon the stoichiometry, the composition of the given material. So if all one type of site, so it is full, the remainder, and how to go to the next other type. Now let me just tell what is the next other type means. So if you have a FCC unit cell which has 4 octahedral site and 8 tetrahedral site. What is this octahedral and tetrahedral? Which is only saying about the arrangement of atoms and their coordination number. It is not about the crystal structure. It is about the arrangement of a particular cation and anion in a crystal structure environment. Okay, it is different from the crystal structure. It is only the anion cation coordination. Okay, if for a specific ceramic, each unit cell has a 6 cation and the cations prefer will be octahedral site. Okay, that is 4 will be in octahedral site and 2 in tetrahedral site. Okay, and now it comes to bond hybridization. The significant covalent bonding you can see there, and the hybrid orbitals can have an impact if significant covalent bond character present in the hybridization. Okay, so for example, in the case of silicon carbide, so the percentage of silicon will be 1.8 and it will be 2.5 in this case. And now if you want to analyze the ionic character present in silicon carbide, it is of 11.5 percentage. Okay, 11.5 percentage is the ionic character of silicon carbide that you can calculate by using this formula. Okay, so that is the 89 percentage of covalent bonding present there. Both silicon and carbon prefer sp3 hybridization. Why? Because both having the number of valence electron is 4, so it prefers to for a sharing perspective to continue. So that's why the silicon carbide will be having sp3 hybridization with a covalent bonding. Therefore, in silicon carbide, which is mostly you can see in tetrahedral site. Okay, for example, predicting the structure of FeO, that is iron oxide, on the basis of ionic radii, what crystal structure would you predict for FeO? So you can see that the cation uh, and their corresponding ionic radius has been listed here, and anion and the corresponding ionic radius has been listed here, and by comparing the ionic radius ratio of a cation and anion, we can actually predict the number of possible coordination number and the possible coordination arrangement, whether it is tetrahedral, octahedral, linear, and triangular. So you can see here for iron oxide and oxygen, the ratio of cation versus radius of cation with respect to anion, it is 0.550. So based on this ratio, we know that the possible coordination number, we already have been seen the list, right? From that we can see that the coordination number will be 6 and the structure will be sodium chloride structure. The structure will be sodium chloride crystal structure. This will be a basically an FCC structure. Is that clear? Okay, fine. Now let me look into the sodium chloride structure, which we call as rock salt structure. Okay, and again here you can see the radius of sodium, which is a cation, and the sodium chloride radius, which is the anion, and take the ratio of sodium chloride and sodium and chloride, that is 0.564. So it prefers, the cation prefers octahedral site, you can see in this case. Okay, and already has been discussed about iron oxide, and now you can see MgO also have the same crystal structure because it have the ratio 0.514, and the cation prefers octahedral site here. So each oxygen has 6 neighboring magnesium 2 plus around that. Okay, around magnesium plus. Okay, now when you look into the structure of a ceramic crystal structure, there are different type of combination you can see. The first one, it is about AX crystal structure. AX means X is the any component. Okay, A means the cation, X is the anion. So you can, the type of crystal structure is NaCl, where A is Na, X is Cl. Similarly, NaCl, cesium chloride, zinc blend, ZnS, and cesium chloride structure you can see here, where the radius ratio of cesium with respect to chlorine is 0.939, and you can see that this radius ratio, it is corresponding to a coordination number of 8. So the cubic site will be preferred here, and cesium chloride has 8 neighboring chlorine around that. Okay, so AX, an example of NaCl, cesium chloride, zinc blend പോലുള്ള structures. Okay, so let me just look into the zinc blend structure over here. So you can see that the ratio is 0.529, and the size argument, already we told no, that radius size argument say that it should be octahedral site. Okay, the cation will be possessing the octahedral site, but you can see that the observed structure, the given structure already there in the screen. In this structure, you can see that the coordination number which is of tetrahedral site. Why? Why? Because the percentage of ionic character is 18 percentage, and the bonding hybridization of zinc favors the tetrahedral site. Okay, so that is a slight change that we already has discussed in the case of zinc blend structure. So that's why a unique structure where the cations will be in tetrahedral site, not in octahedral site. Okay, so that's because of the hybridization between the zinc and sulfur. Okay, and zinc 2 plus has 4 neighboring sulfur over here, and the similar structure you can also see in zinc oxide, zinc sulfide, and silicon carbide. Another type of crystal structure that you can usually see in ceramics is that fluorite structure. Okay, in fluorite structure, as I said, that calcium fluoride an example, where the cations will be in cubic sites. Okay, so uranium oxide and thorium oxide, zirconium oxide, and cesium oxide. So these are the not cesium, selenium, I think. Yeah, CEO2 as of now, which having the anti-fluoride structure, and the cations and anions are reversed over here, and which will be in, the cations will be in cubic site. So another type of ceramic that you will be familiar, that is ABX3 crystal structure, which we call it as perovoscoped structure. So a classic example of that, it is a barium titanate. It is much more a complex oxide. Okay, where you can see the arrangement of barium 2 plus. So, and the center atom will be the titanium cation, and we will be having one more cation as barium that is placed on the corners of the structure, and oxygen making a bond between the titanium exactly. And when you see the corresponding structure is much more a complicated one. So there are three different type of structures are possible: AX, AX2, AX3, ABX3. So these are the three different type of crystal structures that is possible for a ceramics. Okay, now it comes to silicate ceramic. So it is the most common element on earth. Okay, silicate, silica, and the oxide. Okay, so that's why the most of the ceramics are made up of silicate. So here you can example of cristobalite, one of the phase of a silicate. Here you can see the arrangement of silicon and oxygen, and silicon will be on the center and surrounded by the anions, and the structure will be mostly we call it as quartz cristobalite, and tridimite. These are the three possible phases that you can see for a silicate ceramic. And there will be strong silicon oxide bond which will be leading to a strong high melting material as this one. So this is mostly used in production of silicate and most of the kind of glassy material as well. Here you can see amorphous silica, the kind of structure of amorphous silica material that is of glass. Okay, and here you can see that silica 4 plus, oxygen 2 minus, not well ordered in the structure, and the charge will be balanced by hydrogen plus, which we call it as dangling bonds. So it is comparatively stable, therefore unreactive to make good catalytic support. So this is how amorphous silica look like. It has a OH minus bonding also present in the amorphous silica. And now it comes to silica glass. It is a dense form of amorphous silica, and charge imbalance will be corrected with the counter cation sodium. And borosilicate glass is the pyrex glass that is used in lab. So better temperature stabilities are there, less brittle than sodium glass. So our silicon and boron, which are the network formers, and other cations are the network modifiers. Okay, so this is an example of different type of silicate. It is a silicon uh, magnesium silicate and calcium magnesium silicate, where the cations are calcium, magnesium, alumina, which are the cations to act neutralize and provide the ionic bonding present here. And you can see the different tetrahedral arrangement to share the corners and edges and the faces of a different. And these all are silicate elements. Okay. And this is about layered silicate. So layered silicate has clay silicates, and which is of silicon or for tetrahedra connected together to form 2D planes. Okay, so we need a cation to balance this typical structure. Okay, so this is we called layered silicates. And the other one, kaolinate clay alternates. Okay, so it's again a form of silicate where Si2O5s are the layer with the alumina also present there, alumina hydroxide. Okay, so these sheets are loosely bounded by the van der Waals force. So these are different layers of silicates. Okay, and in between you can see the alumina planes and hydrates also present there. Okay, another one type of ceramic which we call carbon black, where diamond is a tetrahedral carbon formulation, which is hard because no good slip planes, and which is brittle, can cut it. Okay, and large diamonds and small diamonds are there, and which is also we can make diamond films. And we know that carbon forms are graphite, which is also we can account in the ceramic list. And there will be weak van der Waals force between the layers will be there, we know that. Okay, and which is normally planes will be sliding easily and will be good lubricant as well. Okay, so different form of carbons we already know, fullerenes and nanotubes. So fullerenes are the graphite sheet by curving into the balls. Okay, so like a saucer ball, you can see that. So these are called fullerenes. Okay, now we'll discuss about defect in ceramics on the other lectures. So we basically today we discussed about the structural aspect, the different type of structures and the different type of combinations and different type of ceramics that we have been discussed today. And in the next lecture we'll be discussing about the crystal defect present in a ceramic material. Okay, so there are different type of ceramics are there, that's already we have been listed, and there are different combination of crystal structures are there, that is also we have discussed. Okay, hope it is clear to you. So if you have any clarification you can ask me. Okay, thank you.